Hello and welcome dear students. So till now we have understood about the ordinary black bolts. So now the turn comes to the second type of bolt, that is HSFG bolt or high strength friction grip bolt. So as the name suggests, these bolts have got very high strength. So the grade of HSFG bolt is 10.8 and 11.2 like that. And also the force transfer mechanism in these bolts is by frictional force, and friction develops between the interface between the bolts and the plates. So such a connection made by HSFG bolt is called slip critical connections. See what happens at service load, since the load is less than the frictional resistance, so there is no significant slip is observed in such connections. But what happens when we use HSFG bolt, because HSFG bolt is also used when we want to avoid the bearing actions or the shearing action of the bolts. So we directly use HSFG bolts, and such a type of connection is called as slip resistant connection. Now this is an ideal type of connection. There is no slip resistant connection as such in real life, because there is always some slip which occurs in every type of joint, whether we use ordinary bolts or we use HSFG bolts. But what happens, we assume that there is no slip occurring at service load specifically, because load is very less, so there is no slip and the joint behaves as slip resistant connection. Whereas at ultimate loads some slip develops, and due to slipping there will be risks of bearing also, and the connection will become bearing type connections. And as we go on increasing the load, slip occurs at particular load, and that value of load is called critical load. Okay, so such a type of connection which is activated from a slip resistant connection to a bearing type of connection at a critical load is called as slip critical connections. Okay, before this value of critical load, the connection was slip resistant connection, and after reaching this value of critical load, the joint becomes as a slip critical connection, and there are chances of slip, and that will occur at this value of critical load, and then the connection will become like an ordinary bearing type of connections. Okay, so in bridges loading and unloading is there, and that causes fatigue, so slip critical connections are not good, so we use slip resistant connections only. And we have discussed all this. Slip critical connections are designed for bearing also, but basically critical load do not reach very easily, and we beforehand only calculate the values of critical load, and we try that the bolts do not experience this critical load. So we design HSFG bolt for this value of critical load. So there are few more principles of HSFG bolts, and in this case the bolt's diameter do not fill completely the hole, because the bolt's diameter is less than the bolt hole diameter. Okay, it means here something is missing. Bolt's hole diameter is greater than bolt diameter, and there is no bearing and shearing at loads, because the force transfer mechanism is by friction, and bearing load and as well as the shearing load is far less than the slip critical loads. So there is no worry at all for these minor kind of loadings. And if HSFG bolt is tightened to a very high load, that is 90% of the proof load. Okay, so the bolts initially transfer the load by friction action till the load can resist the friction, and load, if it exists the frictional resistance, then load is transferred by the shear and bearing action. So this is same before the load reaches the frictional resistance, till that the joint behaves as a slip resistant connection and force transfer is by friction. And if the load exceeds the value of frictional resistance, then the load is transferred by bearing and shearing. So we assume that slip do not occurs very easily and be designed for the value of critical load. So in simple formulas that we have studied till now, horizontal friction resistance is calculated by formula. Friction is mu F into T. What is this T? T is the tension in bolt, or we can say the normal force, and mu F is the slip factor. Okay, just like you have calculated the frictional force in case of mechanics, and frictional force is equal to static coefficient of a static friction or coefficient of dynamic friction multiplied by the normal force. So the similar type of formula it is, and this graph is of not much application here. We can directly come to this formula. Why I am coming to this formula? Because this is given in the code. Okay, and this is how we calculate the slip resistance in HSFG bolt. So why not have a look on the IS code? And this is the IS 800 2007, and here you can read under this title 10.4 friction grip type bolting. So here you can read all the things are written, and we are just directly going to the calculation of slip resistance. So designed for friction type bolting in which slip is required to be limited, a bolt subjected only to a factor design shear force VSF in the interface of connections at which slip cannot be tolerated shall satisfy the following equation. Now we have to calculate this design shear capacity of the bolt. Okay, so design shear capacity of bolt will be equal to nominal shear capacity of bolt divided by the partial safety factor for bolts. So VDSF is equal to VNSF divided by gamma MF. Now we have to calculate nominal shear capacity of bolt, and nominal shear capacity VNSF in the case of HSFG bolt in which the force transfer mechanism is governed by slip for friction type connection, it is calculated by using this formula. So VNSF is equal to mu F into NE into KH into F naught. What is this mu F? Mu F is the coefficient of friction, also known as slip factor. Okay, and the value of mu F is generally equal to 0.55 as per the recommendation given in this code. Okay, now comes NE. NE is the number of effective interfaces offering frictional resistance to slip. So basically it is the total number of shear plane. So in lap joint NE will be 1, and in butt joints NE will be 2. So at the shear planes basically there will be frictional resistance developing at the interfaces. Okay, and the KH is the constant value for different types of holes. Now we have just discussed that the diameter of hole in case of HSFG bolt is more than the diameter of bolt, and bolt do not fill the entire bolt hole. Okay, so if it is a clearance hole or a standard hole, so in that case KH is equal to 1, and if the hole is oversized hole and short slotted holes, then in that case KH will be equal to 0.85, and if the hole is a long slotted hole, then KH will be equal to 0.7. all right. So these are the different values of KH depending on the type of hole. Now comes the value of F naught. So before this we would also like to see the value of gamma MF. Now this is gamma MF, and gamma MF is the partial safety factor. So partial safety factor will be equal to 1.1 if slip resistance is designed at service load. Okay, normal serviceable conditions, whereas gamma MF will be 1.25 if slip resistance is designed at ultimate load. Okay, So at ultimate load we also increase the partial safety factor. Okay, what is this F naught? F naught is the minimum bolt tension. Okay, minimum bolt tension, and it is called proof load at installation, and may be taken as F naught is equal to A and B into small f naught. Now what is this A and B? A and B is the net area of the bolts at the threads, and this is equal to 0.78 pi d square by 4. Okay, and what is this small f naught? A small f naught is the proof stress, and proof stress is equal to 0.7 times FUB. Proof stress F naught is equal to 0.7 times FUB. FUB is the ultimate tensile stress of the bolt, not the plate. Okay, so this is how we calculate nominal shear capacity of bolt, and when we use gamma MF, then we also calculate the design shear capacity of bolt. So this is all about the HSFG bolt, and you can read in this code also. There are so many things mentioned already. And we also would like to inform you that this friction coefficient depends on different types of surface treatments. So basically we take the mu f value is equal to 0.55. Okay, if nothing is given about the surface treatment. If the surface treatment is done in not treated, then we have to use this. Specifically mentioned, it will be mentioned that surface is sand blasted surface after light rusting, so in that case we have to use this value. If the surface is clean mill scale, and then we have to use this value of mu f. So these values of mu f is used also if surface treatment is done, and mostly we take 0.55 if nothing is given. Okay, and of course there are some more things which is to be discussed in this HSFG bolt if you go into deep, and that is the development of prying force, and this is Q. Q is the prying force in the bolt. You see, this is a HSFG bolt. Okay, this is a HSFG bolt, and here it is a tensile force being experienced by these type of connections. Okay, so this plus Q force which you are seeing, this is a prying force, and this is the combined prying force and tension which we study also, but it is not the part of the course, so I am leaving it. And let us discuss from the slide itself that slip resistance, and here also you can see VNSF is calculated by this, where any, you can read number of effective interfaces, value of KH depending on the type of the hole, and F naught is minimum bolt tension or the proof load is equal to A and B into small f naught. A and B is the net area of bolt at threads, and proof stress you can see it is equal to 0.7 FUB. FUB is ultimate stress of bolt. Now it is very easy to calculate the design slip resistance, and we have just divided the VNSF by gamma MF, and gamma MF is equal to 1.1 at service load and 1.25 at ultimate load. So we can easily calculate this design slip resistance in case of HSFG bolt. After calculating VDSF for one HSFG bolt, we also have to multiply it with the number of bolts in the joint. Total number of bolts has to be multiplied so as to get the total strength of the joint. Okay, there are many things to be also included in this, but we do not consider these factors as such for right now. Now this diagram is very important to just for your understanding of frictional force resistance. Now what I have done, I have separated the plates. This is the plates and this is the bolts. Okay, I have separated plates and bolts separated in this diagram, and you can see that it has two plates being applied T force axially, and this is the HSFG bolt, and here tension is developing normally, and this tension is also being resisted by this normal force on the bolt. Now this normal force develops by clamping action, because when you tighten the nut below, then you increase the clamping pressure, okay, and due to this normal force this tension is resisted. But by Newton's third law, action is equal and opposite to reaction. So by that this normal comes here like this. Now this normal is resisted by this frictional force being developing on the interfaces, okay, and this frictional force, this is the normal force, sorry, and this normal force leads to the development of frictional forces. You see this frictional forces sidewise, and similarly on the lower plate, since the normal force direction is reversed, so the direction of force, frictional force, is also reversed. So this is how the frictional force and clamping force are shown here. Clamping forces are normal generally to the plates, and this is clamping force again, P naught, normally shown to the plates, and frictional force develops and frictional force is equal to mu F times the clamping force generally, and this frictional force is the cause which resists the external load which is applied on such friction type connections or slip critical connections. So this is the simple understanding behind HSFG bolts. Now let us also discuss a small numerical of HSFG bolt, and here we are going to use this formula, and all the things are discussed. This is the surface treatment table taken from the IS code, and we can discuss this small numerical problem where we have been asked to determine the shear capacity of bolts in connecting two plates as shown in figure 3.30 if slip resistance is designed at service load and slip resistance is designed at ultimate load. So basically in the part 1 we have to use gamma mf is equal to 1.1, and in second part gamma mf has to be kept 1.25. so this is the simple difference between the two parts. Now what is given? Given that HSFG bolt of grade 8.8 are used, so we can easily derive FUB is equal to 800 megapascal. I said you already that HSFG bolt have high strength. You see this 800 megapascal. Fasteners are in clearance hole, so that means KH value will be equal to 1.0. Coefficient of friction mu F is equal to 0.3, okay, and this is the diagram. 3.30 figure is shown here, and you can see clearly this is a butt joint and with double cover provided. So in butt joint total number of interfaces offering frictional resistance is 2, because it is a double shear case, and here it is 2 rows of bolting being done. So total if you calculate there are 6 bolts, okay, on each of the plate. So if we break either of these 6 bolts then the joint fails, okay. So here although you are seeing 12 bolts, but for failure of the joint you only need to fail the 6 joints on each side. So we just will be multiplying the design strength of one bolt with the digit 6 to get the total strength of joint, okay. And this is gauge, and this is what? Edge distance, this is end distance, and this is pitch, okay. So all these parameters must be clear to you. Again and again I am discussing it. So in the solution the HSFG bolt are having a grade of 8.8. So of course FUB will be 800 Newton per mm square, and fastener is provided in clearance hole, so KH will be equal to 1.0, mu F is given 0.3. So nominal shear capacity of a bolt will be equal to mu F NC KH into F naught. Now F naught calculation is equal to, directly we have used here as F naught was equal to A and B into small f naught, where this small f naught was equal to 0.7 times FUB, So this is what is used here, okay, in this equation. So this is how we calculate the value of F naught, and we have put all the values. FUB is equal to 800 megapascal, and A and B net area of bolt in thread portion will be 0.78 pi d square by 4, and diameter of bolt is 20 mm. So this is calculated F naught, and NE is equal to 2 since it is a double cover butt joint. So VNSF can be easily calculated by this formula. So this is nominal shear capacity of bolt, and if we are asked to get the design capacity of one bolt, and we have been asked to calculate it at service load, so we have to use only 1.1 partial safety factor. So when you use this, you get design shear capacity of bolt, VDSF, okay, and this is the value. So total design capacity of joint will be 6 into this VDSF, since 6 bolts are used on each of the plate. One plate is here and one plate is here, and both are being covered, okay. So 6 bolts are required to be broken for the failure of joint. So we have just multiplied here 6. So this is what the design capacity of joint. Now if we have been asked to calculate the design capacity of bolt under ultimate load, so that also we can calculate very easily just by dividing VNSF by gamma MF. So here VNSF is divided by 1.25, okay. So this is the only difference here, and again we have multiplied this value of VDSF with the total number of bolts, that is 6, and we have got the design capacity of bolt into this, and the unit is here Newton, and we can of course convert it into kilonewton to get this value VDSF final for the joint, okay. So this is how we calculate the strength of joints in HSFG bolts. So this was all about the HSFG bolts, and we will be discussing few more numericals on bolted connections in one more video, and then we will move to the welded connections. So till that, stay tuned and stay safe. Thank you.